Yeah, I think let's get started. So today I plan to finish the sketch of proof of the most of rigidity theorem. And I think that the whole first hour will be devoted to that, maybe even a little bit more. And then we will start discussion of arithmetic groups. I would basically call this like arithmetic, this part of this subject is like arithmetic properties of discrete groups, especially of lattices, since we will discuss both arithmetic, non-arithmetic, and related properties. Okay, so let me remind that this is most of rigidity. That the idea was the following. We start with an abstract isomorphism of the two uniform torsion-free lattices. For simplicity, we assume that the corresponding quotients are hyperbolic, compact hyperbolic manifolds. So this is phi1 of M1, and this is phi1 of M2, right? And my MJs are compact manifolds. So in fact, this theorem is true for both for finite volume hyperbolic manifolds. So what we do next is we, due to our asphericity, we obtain that we have a so like this implies that there exists a homotopy. Okay, I will sketch already. I will skip a few steps. So we aim to prove that there exists a pseudo-isometry between manifold. Okay, yeah, I will write with homotopy. It's a bit better. So F is a smooth homotopy between M1 and M2. This was, so this is homotopy. Yeah, this is obtained due to asphericity of my hyperbolic manifold. So the universal cover is just something contractible to a point. These are two aspherical manifolds, and it turns out that at least I can find a smooth homotopy. I first find some homotopy and then use Whitney approximation theorem, right? All right, then, okay, I will actually denote the steps not as standard implication arrows, but something like that, okay, which is my step arrow. So the next step is to show that there is actually okay, I can lift it to a smooth homotopy of the universal covers. So my gamma J are lattices uniform lattices in POD1, where D is greater or equal than 3. So I want to, I can lift it to the universal covers, and I obtain a map F, I don't know, let me denote it F tilde, between the universal covers. So HD to HD. And our goal is to show that this is a pseudo-isometry. I will briefly explain how to do it. All right. So this is my, yeah, probably I will leave this scheme somewhere there. Yeah, and then I will continue. Okay, so I will use this breadboard. So let me remind that by definition, pseudo-isometry, so a map f between two metric spaces is pseudoisometry. So it is called a pseudoisometry if there exist C and epsilon. Okay, C is going to be greater or equal than 1, right? Epsilon is going to be greater or equal than 0, such that 1 over C multiplied by the distance x between any two points A and B minus epsilon is less than or equal to the distance rho y between the images f of A, f of B, and this is bounded from above by the distance between, sorry, by C multiplied by the distance or x between A and B. I also told you last time that it is a quasi-isometry if I allow in this definition plus epsilon over here. The difference between quasi-isometries and pseudo-isometries is that pseudo-isometries are Lipschitz maps and thus are continuous maps. For quasi-isometries, it is in general, generally it's not true. All right, so in fact, that f tilde is, let me think a little bit. I want to give you something. I want to give some explanation why f tilde is indeed. Okay, so okay, very rough idea how to show that y f tilde is a pseudo isometry. So step number 1, I told you that the fundamental geometric group theory lemma, right? The fundamental lemma of geometric group theory fundamental lemma of geometric group theory, I mentioned it last time, or Schwarz-Milner, known as Schwarz-Milner lemma, implies that gamma 1 is quasi-isometric to HD and is quasi-isometric to gamma 2. In fact, I can already use this to show that. So this implies that f tilde is quasi-isometry. How to show that this is a pseudo-isometry? So pseudo-isometry is a little bit stronger. Again, this is, you will need to think about this a little bit, but this is a good first step. The second step is to see, so fix x, and then notice that x, the map from x to, I think I should take the ratio between, okay, this is going to be a map how should I denote it? I don't know, like capital phi. Okay, so this map from the distance between 2 points, rho of, sorry, no, f of x over f of y. So the distance between f of x and f of y over the distance between x and y is continuous. I only need to think, so this f is a homotopy between m1 and m2. So where f is a homotopy. Okay, let me push it a little bit up. A homotopy between m1 and m2. Then use that the manifolds are compact, and this gives us that f tilde. Well, it first gives us that f this map itself is C-Lipschitz, and then its lift to the universal cover is also C-Lipschitz. Yeah. So this implies that. Huh?
So you have an upper bound.
Yeah. Yeah, I think so. Yeah. So indeed, so yes, f is a homotopy. This implies that f is still Lipschitz, and this implies that so we use that m1 and m2 are compact. Since mj's are compact manifolds. And this implies that phi tilde is also C-Lipschitz. Okay, to be more precise, I think that here the constants are not necessarily the same, right? So, but I mean, eventually we will need this constant C, which we will use for pseudo-isometry definition. Okay, so I will write here some C prime, and here I will write for some C. So this implies that all this implies that f tilde is pseudo-isometry. Okay, this is this step number 2. Okay, again, I will be a bit more sketchy. So this was number 1, number 2, number 3. So the next step is to show that actually this lifts to the homeomorphism. This extends to a homeomorphism of the compactified hyperbolic space. So in fact, f tilde extends to, I don't know, capital F, right, from HD to HD, which is a homeomorphism. This is step number 3. And let me try to, okay, so this was step number 2. Step number 3. Okay, I will mention just a few lemmas, just like to give a, I don't know, a rough idea of what is the technique behind this step number 3. The main result in this step number 3 is the following Morse-Mostov lemma. This Morse-Mostov lemma was, I unfortunately do not remember the state of the art, but it was in a bit weaker, as I remember, in a bit weaker sense. It was proved by Morse. So in fact, Mostov in his paper called it just generalized Morse lemma or something like that. Okay, so let F be a pseudo isometry. In fact, it was shown for quasi-isometries. So let me state it as it is. So let F between HG and HG be a quasi-isometry. Then there exists, okay, this is,
You know that F capital is a pseudo-isometry. Saying that it extends to homeomorphism. Do we know that it's already a homeomorphism on H?
yeah, so in fact, we show first that F tilde is quasi-isometry by using that gamma 1 and gamma 2 are quasi-isometric. And then we prove Lipschitz of this, Lipschitzness of this map, and then you obtain that this ratio is universally bounded by from above by some C. And okay, I'm not really correct.
Does this
It is just universally bounded. So what I wrote here is a little bit messy. Yeah, thanks. Let me correct that.
because there don't need to be some sort of
Since it's compact, it's just bounded. Yeah, it's a continuous
I
map.
think that is enough to get that it's a pseudo-isometry, but my question is essentially, do we know that pseudo-isometries are
Well, this is itself a theorem that if this is a theorem that any pseudo-isometry extends to a self-homeomorphism. This is a theorem. Yeah,
Is it
it's not a trivial.
Do you not have to homotopy the map at all? I believe so. I believe that it is a homeomorphism on the boundary itself. I don't know that I understand why it's a homeomorphism on the interior also.
Oh, okay.
It's doing something.
No, I think it should be homomorphism of the entire compact ball. Yeah,
Right.
it should be a homomorphism of the entire compact ball. I think, yeah, it should be. I hope we will see it from the lemmas I have in my plan. Yeah, but as I remember, yeah, it should be. Here I was a little bit. So this is bounded by C, right? So in fact, P is just bounded by C. Is bounded by some, I don't know, C prime, then fit phi tilde, the universal cover, sorry, this lift to the universal cover is also C bounded. For some C. And this, since this is a bounded map, it implies that just this is bounded. So we see that the F itself is C bound, sorry, F itself satisfies this inequality, right? And then F tilde satisfies this inequality, right? So this ultimately means that F tilde is a pseudo-isometry for some C and yeah, well, some epsilon coming from quasi-isometricity of gamma 1 and gamma 2. Okay. All right. So yeah, let's get back to this step number 2. We have that HD to HD is F from HD to HD is a quasi-isometry. So let it be, I will say that this is a C1, C2 quasi-isometry from this definition from the previous lecture. Okay. Again, recall that there are there is this two-sided inequality. Yeah. I will write 1 over C1 minus C2 and so on. And on the right side will be C1 multiplied by the distance plus C2. Okay. This is the meaning of this C1, C2 quasi-isometry. So then there exist constant.
But there has to be. Sorry. I mean, I can just take some small disk in M and I can collapse the whole thing to a point without changing, without making F not be a.
Okay.
I could just choose, you don't know that the map you get from.
Okay. Your
F1
question was, do we use that it was initially the
Yeah,
homotopy? Okay. Yeah. Maybe I was a little misunderstood. Yeah. So
so yes, there has to be,
yes.
yeah.
Yes.
Essentially my contention is that it's not F twiddle that extends. It has to be,
So yeah, it should
it
be,
has to be some map.
yeah, so it should be a homotopy of HD to HD, such that it's also a pseudo-isometry. Then it extends to a homeomorphism. Yes, okay. So then, yes, then there exists a constant R. So this is a constant depending only on those C1, C2, such that for every geodesic, okay, so yeah, for every geodesic, let me denote it by L in HD, there exists a unique geodesic L prime such that the image of L under F, which is actually an object called a quasi-geodesic, so such that a quasi-geodesic F of L lies in some, well, in our neighborhood of L prime. So geometrically, this means that I have a, well, here, so my L, my image of L is something like that. This is my F of L, right? So it's a geodesic curved somehow, but there exists a geodesic L prime this is my geodesic L prime such that it is contained in our neighborhood. So I hope the picture, sorry, it's L prime, the picture is visible. Yeah. This is the distance from this red is R, right? It is bounded by distance R from my red line L prime. So roughly speaking, I have a geodesic that in some sense, well, coarsely approximates my quasi-geodesic, right? This is the generalized most of lemma. Okay, then the second step is the following. So the second lemma. If F is a pseudo-isometry, okay, it is pseudo-isometry. I will write a PI for pseudo-isometries, okay. But I think it's still true for, oh no, probably I already need here pseudo-isometry. So then there exists again some constant R, so there exists some R greater than 0, such that for every geodesic, for every geodesic L in HD, and every hyperplane and every hyperplane orthogonal to L, the image of this hyperplane, okay, so in fact, I need to draw a picture and then probably say what do I mean. In fact, I'm going to project f of h on my geodesic L prime from the first lemma, and I'm going to say that the image will be like some arc of some bounded length. So let me draw a picture. I have okay, the image f of h projects onto an arc onto an arc in a geodesic L prime from Morse most of lemma, and this arc of length less than r. Okay, so let me now draw the picture. So I have a map okay, I think I need colors. So this is my geodesic L, and okay, suppose that I have a hyperplane. Well, it's probably is going to be complicated. Okay, so let it be my hyperplane. Now I act by F, and I see what is going on here. So what was the color? Yeah, okay. So my image is something like that, right? But I have a red geodesic approximating. So this is my L prime approximating my image of L, right? And this green hyperplane H its image going to be something also like curved. So I'm trying to this is my h, I don't know, this is denoted by f of h. And then I need to project my blue image on this red arc over here, right? I don't know which colors can I use, but let me try. So suppose that this is, I don't know, in some sense, the outermost points from somewhere. So let it be my orthogonal projection from this hyperplane onto this, right? So this lemma states that I can choose in advance this constant r such that this arc here, this geodesic arc, is of bounded length. Yeah, so this, so I mean that f of h cannot be like too much distributed in this ball, right? So this length is, this geodesic segment is of length less than r. Okay, yeah, I hope the picture so far is more or less clear. All right, then yes, okay. So in fact, yes, I think that yeah, I think that you're right. I need to use the fact that it was a homotopy. Then this fact together with homotopy implies that, so this fact together with being homotopy implies that my pseudoisometry extends to the homeomorphism. How to use this lemma over here? The idea is that the boundary, we can use the topology on the boundary. Okay, we can identify the boundary as the set of equivalence classes of actually geodesic or quasi-geodesic rays, right? So I will just write here the idea how to use this. So then we use that the ideal boundary is the set of equivalence classes of quasi-geodesic rays. Quasi-geodesic rays. And well, okay, technically I should fix a point, right? And I choose quasi-geodesic rays coming, I will say, like starting from this point and going anywhere else. And I need to take only those that are not so in one equivalence classes, they fall in one equivalence class if they are of bounded distance between each other. And basically so we use that, and then we like change, we can parameterize L by, I don't know, as like L of t, and then my hyperplane can be also parameterized as h of t, moving closer and closer well, in some sense, to one of the endpoints, right? So essentially, this lemma shows that the image of this h of t will always be bounded, and this means that, in some sense, like the entire half space, I know it converges to the limit point of this L prime. And I'm not sure, but probably, yeah, probably it's, yeah, I think that it's enough. So, and then, okay, and then apply previous lemma. Previous lemma to L of t and h of t, where t tends to infinity. So basically consider this situation. This gives us that F is a homeomorphism. Well, technically you will show that, if I'm not mistaken, we will use that the compactified space is compact, it's Hausdorff, and probably we will show that it's a bijective continuous map to the compact Hausdorff space. So it's, well, from compact to compact, it's definitely should be a homeomorphism. Yeah. This is, again, this is a rough idea. In fact, the proof of this lemma is based like on a 2-3 lemmas. Then this is also, you need to do some geometry here to show that. And this step is also some work. Yeah. But at least I hope that you now see the picture. All right. So this was step number 3, which explains that F tilde, which was initially homotopy, extends to a homeomorphism. All right. Now,
If that's a homeomorphism, I still don't think that it's a homeomorphism interior. We just haven't changed the map of the interior at all. If it's a homeomorphism on the interior, then the original F between the two is homeomorphism. That's just
okay, I will leave the question, but I'm still pretty sure that this should be. But okay, question. So the question is homeo only of boundary, right? But I think that this should be a the homeomorphism of the entire compactified space. Okay, yeah. Next step number 4 is that F actually is a quasi-conformal. Yes, it should be like quasi-conformal map. Okay, yeah, I'm not really correct in what I'm saying. The boundary map, right? Now I have a map from the compactified space to the compactified space. And now I want to consider its restriction on the boundary. It is a homeomorphism. So I want to show that it is actually a C quasi-conformal map. So GF from DHD to the boundary of HD, which is D minus 1 dimensional sphere, right? Is C quasi-conformal. Now, what is the definition of C quasi-conformality? Yeah, in step number 4. Okay, I will. Okay, I will write like formal technical definition, but I will just draw a picture which explains that. Okay, since it's a little bit complicated. So a map F a map F from X to Y. Okay, this is a definition. A map F from X to Y is say quasi-conformal if there exists C, like if there exists number C greater than 0 such that for every X in X, the following ratio has a limit bounded by C. And so I will write it as follows. The limit, okay, as R tends to 0, then I have here supremum by, okay, this is even a bit hard. So I'm taking the supremum by a sphere, by points from a sphere. So supremum by A from X, such that the distance between A and X is R, right? And supremum of which number? Row Y, F of A, sorry, F of A and F of X. And here I divided by infimum like along the same set. So also the distance between F of A and F of X. So if this limit exists and is bounded by C. Now I need to draw a picture. So I have a, in fact, we consider the image of the sphere, or I can consider just a ball centered at A and its image. I will say that I have something weird, which is the image of this ball. Okay, this orange itself is just the image of the sphere. So I will write F of the ball centered at the point A and of radius R, right? This is its image. Yeah. Okay, yeah, it's centered at X, right? Yes, it's centered at X, thanks. So this ball is centered at X. I take its boundary sphere and I consider its image. I can find two balls. Okay, one sphere inscribed, and this gives me the infimum, right? And I can find R, so this is going to be R1. And I need another color. And I have another ball. Okay, maybe it doesn't look like a ball, but yeah, it should be from the same points, right? And this is, sorry, R2. So R1 and R2, and I guess that this point is f of x, since it's centered at f of x, right? So basically, my quasi-conformality means, so it means that the limit of R2 over R1, right, is bounded by C. So the ratio of this, okay, of R2 over R1. So again, it is deformed, but not too much. Yeah. This means conformality. As we remember, conformal maps, they they send spheres to spheres, right? But quasi-conformal, they can somehow, yeah, they can make it worse, but not too much.
Definition of this in terms of like this being like
This one,
the definition of that I know is preserves sort of infinitesimal angles.
yes.
Is that sort of the same?
Probably you can, yeah, probably you can also say that angles are not, so again, they're not preserved, definitely, but you probably change, probably like the sign of angle is bounded also by some constant. Yeah. Probably you're right. Yeah, so this is a geometric interpretation of this. And then step number 4 basically is to show using, again, well, it's based on the previous lemmas, but you show that the boundary map is indeed quasi-conformal. And then we use another delicate result. So, okay, let me state first. So lemma our f, our df is indeed C quasi-conformal, and this is also based on, again, it's basically based on lemmas from step 3. Right. Finally, the next step number 5, I will need this word. Okay, well, right here. Step number 5 says that for n, okay. Okay, basically, I will say the following, that is that df is actually differentiable almost everywhere. But what I want to say, okay, the step number 4 is that the differential of F is quasi-conformal. Let me say this. And step number 5 is based on the following theorem. Okay, so let n be greater or equal than 2, and let F be a quasi-conformal homeomorphism of Sn to Sn. And F a quasi-conformal homeo from Sn to Sn. Then F is differentiable almost everywhere. And it is important that, moreover, the differential of this, sorry, it should be just some small f. And this differential of f, the differential of this f, is uniformly bounded from both sides. So, moreover, there exists, so it's uniformly bounded, there exists some lambda greater than 1, such that for almost every, okay, I will write it, for almost every point x in Sn, and for every v in the boundary, in the tangent space to x, we have the following. We have that the ratio of the norm dx of v over the norm of v, so this ratio. Well, basically, I just take the a linear map, right? A linear operator in this case, and for any vector v from the tangent space, the norm of the image of this v under this linear map over the norm of v is bounded from above by this number lambda, and from below by 1 over lambda. See, this is not true in, and this is very important. So remember that my quasi-conformal map on the boundary is of dimension d minus 1. So if dimension d is starting 3, then d minus 1 is at least 2, right? So for at least 2, for the dimension of the sphere, at least 2, it is okay. But for S1, this doesn't hold. So for n equals 1, we have basically homeomorphisms such that the differential whose differential is 0. There are homeomorphisms of a circle with differentials being equal to 0. So you cannot bound bound this ratio between the numbers around 1. Yeah, that's the idea. So basically, this bound, it separates the norm of this thing from 0, right? It separates it from 0, and this is very important. All right, I think this is time to make a break. And then I will continue. Where here, first step?
Like I don't understand why that implies F tilde is
Why F tilde is quasi-isometry? Or-
like F tilde is pseudo isometry.
Yeah, it follows from the fact that it's quasi-isometry, so it satisfies this two-sided inequality, but plus some constant. But then you show that it should be Lipschitz. And you show that it's Lipschitz by showing that this map is bounded. And this map is bounded since this map is continuous, and initially this is a map F on a compact manifold. But every continuous map on a compact set is bounded, right? So then you use this bound to lift to the universal cover, and then you use that F tilde is also C-bounded, and then you show that actually F tilde is C-Lipschitz, right? So it is C-Lipschitz and thus F pseudo-isometry. Okay. Yeah, okay, now let's make a break. All right, so let's continue. I will begin the second half with a remark regarding this question. I was indeed a bit wrong here. Thanks for being very careful. So F tilde extends to a continuous map such that the boundary map is a homeomorphism. So let me clarify my writing here. So F tilde extends to in continuous continuous map such that df from dhd to the boundary of hd is a homeo. So like essentially there is this theorem. So if I have a smooth homotopy between two compact hyperbolic D manifolds, then this smooth homotopy lifts to some well, I mean there are actually many lifts, but then each of its lifts extends to a continuous map of the compactified space, hyperbolic space to itself, such that its restriction on the boundary, which we say is a boundary map, is a homeomorphism. Right, yeah, thank you very much. It's very important. And yeah, I think that otherwise it would be indeed a bit easier to finalize like the proof of this entire theorem. So we just mentioned that step number 4 then gives that this boundary map is C quasi-conformal, and this implies that the differential of the boundary map is also C quasi-conformal. I will just select to clarify this step number 5. So the step number 5, it gives us the function is differentiable and it's bounded. Its differential satisfies this boundary condition. But in fact, there's the following theorem, which I will just mention without any proofs or something. But let me switch to the right board now. So there is the following theorem. So if F, okay, I think that let f, yeah, actually, there will be two parts. Okay, sorry, I will move it a little bit. So theorem, part number one, let f belong to the group of self-homeomorphisms of, I don't know, S. I can just write Sn, but in fact we mean Sd minus one, right? And assume that it is differentiable on how should I denote differentiable? I know C1, right? And C1 on the also on this N, right? Okay. Yeah. Then there is the following equivalence. Then F is, I will use the constant K. It's K quasi-conformal on Sn if and only if its differential is also K quasi-conformal. Sorry, K quasi-conformal. So I'm writing K Q conformal where on the tangent bundle of Sn, right? Obviously. This is the first part. The second part follows then from the fact that f is quasi-conformal. So if f is quasi-conformal, but differential is just conformal, then f itself is going to be, so if f is Q conformal on Sn and differential is just a conformal, okay, again, technically I should write it's extended conformal, right? On the on the tangent bundle, right? Then this implies that f is a conformal or anti-conformal map of the sphere to itself. All right, so we are going to use this just to pass to the differential. And now our goal is to study the differential of the boundary map, right? Okay, so great. So the next step is just to draw a picture and to see what's going on here now. So I will use again the ball model for the hyperbolic space. So what I have here is my S d minus 1, which is the boundary of HD, right? And now I choose some point here, and I have a tangent space and some ball centered. So this is X. This is Tx as d minus 1. And this is my ball, I don't know, of radius. Well, in fact, I can take the ball of radius 1, I guess. Okay. And I act by F, but on the top, I have another arrow, which is the differential. Okay, more precisely, in our case, so denoted as df, right? It's the boundary map. I denote it as the capital F. So technically, I should write here differential of df. Yeah, well, maybe it's a bit too much, but I hope it's all clear. So quasi-conformality and differentiability implies that I have, so this is a linear map. So I still have a tangent plane or tangent space over here. So this is now my tangent space with respect to the point df of x, right? And still of the boundary sphere. All right, so this is my point dfx, okay? But since my df is differentiable and quasi-conformal, I have an ellipsoid basically in the image, right? The image is an ellipsoid. So this is an ellipsoid, which is the image of my ball. I will say that it is d. Okay, sorry, it's d of df of the ball, right? Yeah, an ellipsoid. And this ellipsoid has its axis, right? Find its axis. I can write that v1, v2, and so on, which depend on basically on df of x, right? Okay, yeah. I can say like it's the longer one, right? Then I can choose some order or something. So it has axis. I mean the numbers basically depending on the coordinates of the point d of f of x. So it has axis of length. I will write of length v1 of df of x, v2 of df of x, and so on. Well, essentially it's dimension d minus 1, so I have v d minus 1, the last one. All right, then I define the, and this thing is very important, so I will highlight it by orange. Unfortunately, I forgot how is it spelled. I need eccentricity function. It's ECC, right? Correct? Look, yeah.
I think so. Looks right to me.
Not X here, or both are.
No, I think it's two C's.
Okay.
Actually, let's.
Okay. Eccentricity function, and this eccentricity function is E Okay, I will denote it as like mm, okay, yeah, thanks. So I will denote it as just E sub f, since it essentially depends on f, right? E sub f of x, and this is going to be equal to the maximum by I not equal to j with the following ratio, where I have the norm of vi. Okay, it depends on df of x, right? 1, 2, 3, and then this over vj. Okay, again, depending on the same point, right? So I basically just write down, I can just write that this like the longer one divided by the shorter one, yeah? So this is my eccentricity function. All right, this eccentricity function is very important, since that this is something which is also differentiable almost everywhere, right? Okay. Let me. Yeah, I will write down here. Okay, so one can notice that EF is in fact, so EF is what is going on here? EF is differentiable almost everywhere, and is gamma J invariant just by the construction, since, well, we started from the homotopy, right? That appears as basically as an extension of an isomorphism of our fundamental groups. So these objects are, by the construction, gamma invariant, where gamma is a lattice isomorphic to one of this. Yeah, so it's gamma J invariant. Where I can say that it's gamma 1 invariant. Okay. Yeah, this is very important. Then we will write the following lemma. Gamma x on SD minus 1, which is the boundary ergodically, right? We already mentioned this. It follows from the Hobby-Moore ergodicity theorem, right? From Moore ergodicity theorem. I think I shouldn't remind, right? It's I will just write that recall follows from the Moore ergodicity theorem, since P, which is the group of Euclidean similarities, acts on G mod gamma ergodically, and then gamma acts on G mod P ergodically, and this is precisely as D minus 1, the boundary. All right, so this is the proof of this lemma. Since, okay, now I have a nice function, which is gamma invariant. And due to ergodicity, we have that EF. Okay, so EF is constant. I don't know which constant. C almost everywhere, right? So it's a constant almost everywhere. The question is, which constant? Okay. If EF is equal to 1 almost everywhere, then we are done. Since then we obtain that DF. Okay, to be technically correct, the DF is conformal, right? So if this function, yeah, look here, it means that actually almost everywhere it's a ball. But if it is almost everywhere a ball, then well, it will be a ball in some like neighborhood, in some open subset probably, and then this is going to be just a conformal map, right? So then this is a okay, it's an element of the conformal map on the tangent bundle. So I need to show that in fact this constant is indeed 1. So if it is 1, then it's good. In general, if C is not equal to 1, I can find in this ellipsoid, I can like pick K smaller than D minus 1, like the most long axis, right? If C is not equal to 1, then pick K strictly less than, well, I mean, certainly if it is not equal to 1, then I have D minus 1 in total axis. So I choose some number of longer ones. We know that they're not equal to each other. So this number should be strictly less than D minus 1. Then pick K less than D minus 1. Most, okay, longest, right? Just longest axis of our ellipsoid. This gives that we have a k-dimensional invariant, gamma invariant plane. Gamma can only permute the equal longest guys, right? It should preserve the longest, it cannot. So this gives us a gamma invariant, okay, a gamma J invariant k-dimensional plane U, right? And in fact, the entire bundle over U, right? The whole gamma invariant bundle. Okay, then what we do next? We say that then we have the Grassmannian, basically the space of k-dimensional planes in the bundle, right? So then this means that I have the Grassmannian, the space of k-dimensional. So this is a space of k-dimensional planes in the tangent bundle of SD minus 1. And this is the quotient of my Lie group of isometries G over the subgroup HK, which depends on K, where this HK is in fact the stabilizer of G, of this plane U. And this is a subgroup. Actually, this is a subgroup of P, where P is the stabilizer of some infinite point, right? So definitely this stabilizer of some plane containing infinity, some fixed point at infinity is a smaller subgroup, right? Well, we just use, again, we will just use that it is a non-compact subgroup. Non-compact. So we have this. But then by the Moore ergodicity theorem, gamma acts ergodically again on this quotient. And gamma acts ergodically on G mod HK, right? And this implies that, yeah, this is not possible, right? Which is basically a contradiction. So yeah, and gamma acts ergodically again by Moore ergodicity.
Sorry, that Grassmannian, is that the Grassmannian of rank K sub-bundles of the tangent bundle?
I'm only not sure. Should I choose the unit tangent bundle? Maybe so. Yeah, I'm taking.
Oh, you're doing it, I see. We're taking the Grassmannian pointwise.
Yes.
So you have a bundle, okay, I was. So
So it's a
you're
bundle
out
over U, right? It's a bundle
looking
over
at the
U.
bundle fiberwise. That's what you're doing.
Yes.
Take the Grassmannian fiberwise. So it's going to be a fiber bundle over the same base.
Yeah, it's going to be a fiber bundle over U, right?
Yes.
So
So
this is a fiber bundle over U. This thing. Yeah. Okay, so let me say something here. I'm not sure where can I raise. Okay, I will raise here. Maybe I can just say. Okay, yeah. Let's switch. So we showed. Okay, essentially what we obtain here. This gamma acts ergodically on this fiber bundle over U. And this, in fact, means that I have a, okay, so yes, I have this invariant bundle, right? With this invariant bundle, I can probably, okay, I can probably consider the angle. Yeah, so basically I want to say that I cannot have, yeah, so it should be of like, it basically should be of zero measure, yeah. So I cannot have non-trivial gamma invariant, right? Yeah, I cannot have non-trivial gamma invariant, but maybe one needs something a bit more. I think I can say something like that. So if I have a gamma invariant section, right? Okay, where can I, let me, okay, I'm here. Let me raise this. Okay, so yeah, I will use my old notes. So if since gamma acts ergodically, here I have some gamma. Okay, yeah. So gamma acts ergodically on where G over HK. This implies that there exists a non-trivial gamma invariant okay, technically this should be k-dimensional, right? K-dimensional. Can I say vector field? No, I can say that sub-bundle, right? Right, yeah. So generated by some vectors, I don't know, v1 to vk. Then I can probably define the functions that take okay, technically I should take 2 points that are not. So then for x not equal to y, we take translations along geodesics from x to y. We consider translations but translations in the tangent bundle. So these are going to be okay. This should be p yx from ty sd minus 1 to tx sd minus 1, and then we define the functions which we will denote by Vij from the product. So this is going to be, the function will be defined as follows. I am taking 2 points, x and y, and I take the scalar product of vi of x and p yx of vj, right? Applied to vj of y. So this is my map from S. Okay, this is the map from the product, right? SD minus 1, SD minus 1 to R. Then the fact that gamma acts ergodically on SD minus 1 implies that the diagonal of gamma acts also ergodically, and this is ergodically, on the product SD minus 1, SD minus 1. And this implies that these functions, which are nice, measurable, differentiable functions, these functions are constants almost everywhere. So it's constant with ij almost everywhere. Yeah, now I want to define, so like there is an angle, which I can say that it's invariant, but I basically want to use the Gauss-Bonnet theorem. I want to take 3 points now, x, y, and z, and like find the projection of Vj and just compute the composition of those translations and see that I get first something bounded, but maybe it's not. Okay, this is a little bit long. I wanted to give like a very short sketch, and this already is taking more than I expected. Okay, so geometrically, I have a bundle, right? I have a rotation along around some. Okay, yeah. So let us, I think, let me finalize it in the next lecture. So what are the next steps? The point is that I have some invariant plane, right? So basically what we want to show that I cannot have anything, I cannot have a proper k-dimensional invariant subbundle, right? I want to show that it should be, well, it should be either 0 or, okay, it should be basically everything. So the fact that it's not, okay, so what does ergodicity mean, right? Ergodicity means that if I have a non-trivial, if I have a gamma invariant set, it should be either of the full measure or it should be of 0 measure. Maybe I can just make it shorter and say that if it is not, okay, again, if it is a full measure, then k probably should be just d minus 1. So an issue is that when it is of 0 measure, yeah. So I can probably assume that it's okay. Yeah, let's let us finalize this. Or like, so it remains not that much, but I want to make this last. Actually, I want, since again we've made many steps very sketchy, the end of this argument should be a bit more clear. So I want to show that, okay, probably there are a bit, there are a little bit different approaches to that. So either I consider these functions and then I analyze how this translations. Okay, basically I need to find the. I will probably find some triangle such that like my path along this triangle gives me something that contradicts ergodicity, or I will just study the if I can probably assume that if it is of 0 measure, it's just one dimensional. Okay, I will do it next time. Then yeah, so if it is the full measure, it's indeed everything, and then we are good. So I just need to show that I cannot have something of 0 measure, and that's, yeah. Okay, I think let's indeed move it to the next lecture. So I will write. We will continue next time. By the way, yeah, I will have, so next week we will skip, right? So we have next lecture on Thursday and then one more lecture on Tuesday. That's the plan for just probably 2 lectures. Okay, yeah, thank you. And
Is this part?
I
Is this part like step 6?
yeah, this part is already step 6. indeed. Yeah, thank you. Let me just, right, so this, I will say that step number 6 already starts here, right? So step number 6, and let me switch to the left just to record it. So my step number 6 was to show that basically I showed that the eccentricity EF is constant, right? And the step number 7, which is the final one, right, is to show that this constant is actually 1, right? Almost everywhere. And this is almost everywhere. And then this is the end of the proof, right? Since this implies that DF is, since then GF is conformal, and then F itself is in isometry. Right, this is the plan for step 7. So what we already have, we have that it's constant almost everywhere. Then I want to give a little bit more careful argument that I cannot have a non-trivial proper k-dimensional invariant, gamma invariant subbundle. This is the most important thing in this step number 7. Yeah. So the step number 7 will be done next time. Yeah, again, I think that I made it actually a bit differently a couple of times, but it really requires maybe 10 more minutes to finish. I don't remember these details, unfortunately, with angles. I will try to recover this. Okay, thank you for your questions and for your attention. Yeah, I have corrected some important statements here. Thank you.